Welcome back to the next part of the JUNIPER Consortium's research meeting this morning. And we now have Dr. Lorenzo Pellis from Manchester, who will be speaking to us. So his research interests are in the use of mathematical models to describe how infectious diseases spread and evolve. So his main interest areas are in populations with social networks, multi-scale models, and statistical methods for parameter estimation. And since the pandemic broke last year, Lorenzo has been working in developing, it's been one of the teams in providing weekly projections for the R value. So I think he's going to talk to you a little bit about that this morning, and more generally about the challenges that they've had in trying to do these projections for COVID-19 dynamics and how they're informing the UK pandemic response. So with that, thank you very much, Lorenzo, and I'll pass over to you.
Thank you very much, Kira. Can you all hear me?
Yeah, we can hear you. We can see the slides.
Fantastic. Thank you. Yes, so I'm a Sir Henry Dale Fellow at the University of Manchester, and this is one of the things that the University of Manchester has been doing throughout the past year and a bit is trying to estimate the reproduction number and provide short-term or medium-term projections of the epidemic trends. And this is what I would like to talk about. Like in general, when people present their work, it's a lot of polished work, but I really would like to kind of dedicate some of the time in stressing the challenges and the things that haven't necessarily gone that well. And I think this is important because this is a struggle that we all go through, but it's rarely discussed extensively during talks. So this is work done with a lot of other people, and I can't thank them enough. So so I'll briefly describe give a sketch of the UK pandemic response for those of you that are not really used to it or that are watching us from another country. And the model that I've been talking about is a model of it's fundamentally a hospital-focused model, but I'm using it to estimate the reproduction number as well. So it's a model that combines some detailed description of the hospital pathways and also some transmission outside of hospital. And it might also help shed some light on this estimation of our procedure. That could be helpful for people that have heard a lot about R in the news, but also could be helpful for other people in JUNIPER because different people have used different models, and because it's all really moving very fast, there hasn't been, in my opinion, as much the time to kind of discuss each other's model and understand a bit better what other people do. This makes it better to some extent because the different estimates tend to be kind of independent expert opinions, but I think it's important that as the urgency of COVID goes down, then we start resuming talks more on a scientific level of what different models do. So this is going to be a hospital-based model, and I'll describe the within hospital length of stay, and then I'll move to the population level model structure and then discuss the data that I'm using and how I'm fitting them. And the goal of this model is to provide short-term forecasts of epidemic trends and estimates of the reproduction number. But I would like to focus mostly on the struggles that we have been experiencing with this model. And if time permitting, I'm going to discuss a little bit about the work leading to the first lockdown and how some of the ideas that I discuss have been instrumental at that level. So the UK pandemic response is highly structured. As Julia and Matt mentioned at the beginning, JUNIPER contributes heavily into SPIM, the Scientific Pandemic Influenza Group on Modeling. This is a group of mathematical modeler and experts in infectious disease epidemiology, and then they provide a consensus that goes to the Scientific Advisory Group for Emergency, or SAGE, which then informs the Prime Minister and the Cabinet Office Briefing Room, also known as the COBRA. And one of the important things that SPIM does on a regular basis every week is to provide some medium-term projections of epidemic trends and the estimates of R and the growth rate. And the idea is to estimate how the epidemic is going to proceed in the absence of any changes. So in the graph to the left is that if we provide our short-term projections at the time of the yellow line, then the model is going to continue growing exponentially, because that's what you've basically seen up to that point. Even if we know that a lockdown is going to come and therefore numbers are going to go down, what these short-term projections will show is just the model continuing growing exponentially, because it's very difficult to forecast exactly what the impact of any control policies is going to be. Now, after 3 lockdowns, we might have a slightly better idea than we had at the beginning, but it's still, every lockdown has appeared in a completely different context. And the one in November didn't have schools closed. The one in January had vaccination going on. So it was, every time it's a bit different. So it's very difficult to predict the impact of any control policy. So these are all predictions in the absence of any changes, to see what would have happened if we hadn't done anything. It's a rolling situation, so the response has been very fast at the beginning. The model was set up in days. The idea is that this is repeated every week, and it's also a moving target in the sense that for something that is repeated, that has been repeated every week for more than a year, the amount of fiddling work that is done on a weekly basis is quite stunning, I have to say. So the model keeps being adapted. The new data comes in with new challenges, new questions arrive, so the model needs to kind of address slightly different questions and so on. I would like to stress that this is a team effort. JUNIPER has shown how many people there are working together. This is very much of a team effort, and that means that the model doesn't need to capture everything. And the model, you can get stuff wrong because there is the help of your colleagues that can cross-check what you've done and see whether the opinion of different people kind of coincide. And all the models have been combined. As Julia showed, there was quite a lot of there are quite a lot of models that come into these estimates of R, and then they combined into an overall output that is produced as the official estimates of the reproduction number and the growth rate as well. So very briefly discussing the model, the model is fit to 2 different data streams at 2 different scales. So we're using the chess data set, and now it has changed names, but fundamentally it's a model of COVID-19 hospitalizations in England, and includes individual level patient data. So it's very detailed, but it's also incomplete. So it doesn't really cover all hospitalizations in the UK. And it looks pretty much like what's shown here. This is an example. This is, of course, made up data by one of my postdocs, Chris, who's been working quite a lot on this, and most of the credit of analyzing this data set goes to him. And although he's certainly a name you can trust, what should appear really under trust name is typically like the Manchester Foundation Trust, or whatever trust is managing the hospital where the admission is occurring. Then you have some information like the sex and the age of the hospitalized person, when that person was hospitalized, when it moved to ICU, if it moved to ICU, when it went back from ICU into the hospital, and when it was discharged. So this is very detailed data about the pathways that each individual follows, but it's incomplete. The other data set we're using is the situation report for the NHS, that provides the number of daily admissions and bed occupied, but it's complete data, or roughly complete at the national level, but it doesn't really provide much information about how long each individual is spending in various compartments and who is where. It's just a number of admissions, number of hospital bed occupieds. And it looks a bit like the one at the bottom where we have some information about how many people have died in hospital, how many people arrived in hospital, tested or not tested, and what's the number of bed occupied. So using the information from the CHESS data set, what we did was to kind of look at all the different pathways, or at least the most relevant pathways that individuals follow. So although at the peak of the pandemic, there were a few people who were arriving basically straight into ICU, most of the individuals first arrive in hospital and then proceed to ICU. Individuals from ICU could die or could step back to the hospital ward in a monitoring state and then maybe being discharged. Very few people go back to the hospital ward and then go back to ICU, so we have ignored that. And then hospital some individuals get discharged from hospital without going to ICU if they're not too severe. And some individuals are also dying in hospital without going to ICU, possibly because they are considered too old to actually survive the ICU, which is very disruptive, physically for the individual. And so with this, we can estimate with some information about how many of these transition and pathways we see, we can estimate the mean duration along each of these paths and the standard deviation of that duration. And this is a key piece of information because that's tell us how long it takes between admission and discharge, or admissions and ICU and so on, which is crucial to inform the model. However, estimating these durations is by no means obvious. This is a common challenge in infectious disease models. You're interested in estimating the time between two events in hospitals, but it could also be two events like between infection and onset of symptoms, or between onset of symptoms and hospitalization. You always have these two events, and then sometimes you can observe the first event and you don't observe the second. So you might imagine that the individual, you can tell the model that the individual has had the first event but has not really gone anywhere else. So you know that a second event is coming, but you don't know when it's coming. But in many cases, for example, when you try to capture the onset of symptoms, you do not have in your data set individuals that have been infected, because you only observe once they have symptoms. And so you don't have this kind of right censoring problem. Instead you have a truncation bias, where individuals that have gone through the first event but not through the second are just excluded from your data set. And this creates some problems. So what I'm trying to say here is that, look at this graph at the bottom. If someone arrives in, for example, if someone gets infected at this point and then has onset of symptoms at that point, then you see them in your data set. But because you only observe an individual when the second event has happened, individuals that have a long period of time between the first and the second event just don't really appear in your data set. And individuals that have a short time between the first and the second do appear in your data set. And therefore your data set has an overrepresentation of shorter durations and an underrepresentation of longer durations. And this is particularly acute as a problem if you have an epidemic that is growing, because the vast majority of the recently infected people, the vast majority of people in your data set are all recently infected, and therefore you will only see the ones that have the shortest time intervals and not the longest time intervals. So one way of accounting for that is to kind of condition on observing the second event. And this is basically a way of inflating the distribution that you would naively observe by kind of correcting for this, for the lack of longer durations in your data set. And the difficult part is that this kind of overrepresentation of shorter duration or underrepresentation of longer durations really depends on how the epidemic is going, whether it's growing or whether it's declining. Because if it's declining, the vast majority of your individuals have been infected a long time ago, and therefore this problem of underrepresenting longer durations is much less acute. So with all this information and these methods, we could estimate the mean and the standard deviations of these time intervals. But notice that the duration, for example, between going to hospital and being discharged or dying is about 8 to 9 days, but between hospital and ICU is about 2.5 days. So most models typically follow this this competing hazards approach, where if you're in state 1, then you could proceed either to state 2 or 3 with 2 different rates. It's completely equivalent to represent this model with an overall rate of leaving state 1, which is the sum of these 2 rates, and a certain probability of going in one direction or another. But these are all called competing hazards. But what appears from this data is that the time one spends in hospital really depends on when they are going next. So what we use in this model is a slightly more refined approach, where you are in state 1, but you are distinguished between whether you will proceed to state 2 or proceed to state 3. So this model now, this approach now has 3 parameters. One is the probability and 2 rates. So it's a little bit more sophisticated. It has more parameters than these previous 2 descriptions, but it has the positive aspect that, first of all, it captures the duration in state 1 a little bit better. But more importantly, in my opinion, first of all, it's more easily parameterized with the data. And second, is it really distinguishes between processes that are conceptually different. For example, if outside of hospital somebody gets infected and then it takes about 7 days for them to recover, this is just a natural progression of the disease, of the infection. If instead somebody gets infected and then they go to hospital and it takes about 2 days to go to hospital, then the speed of that process depends on hospital seeking behavior, which is very a very different process, conceptually different process. So the model we ended up with is a model of this form. There is a susceptible individuals. They could be, with a certain probability, they could be asymptomatic, and they proceed along this route here. If they are symptomatic, we know that they are incubating the infection, and then there is a stage of pre-symptomatic transmission where they don't have yet symptoms, and then there is a late phase. If they don't go to hospital, there is a late phase where they do show symptoms if they are not along the asymptomatic path. And we have information between infection and onset of symptoms, and we know that it's roughly of a gamma 3 shape. So it's not an exponential distribution, it's slightly more concentrated around the mean. Then individuals might follow this route and then recover, or they might go to hospital. So these are individuals that show symptoms, and we know they will go to hospital. So these two are apparently indistinguishable, but we separate them based on where they are going next. And then individuals that go to hospital could be in hospital and then die, or could be in hospital and then go to critical care, or in hospital and then recover. And those that go to critical care, they could be in critical care going to die, and critical care going to stepping down back to hospital in a monitoring state and then recover. So separating, as I was explaining before, separating these, the individual wherever they are based on where they are going next is one of the key features of this model. All of these rates of progressing are informed by the chest data set, as I've described before. And what we achieve by fitting to all the data streams is to estimate the probability of going to ICU, the probability of dying if you're in ICU, the probability of dying outside of ICU. And instead, the probability of ending up in hospital or probability of being asymptomatic is taken from the literature. So some examples of results of this model. This is what happened when we originally fitted to the first wave of data. We were doing this regularly every week, but this is just a snapshot of what happened if you fit to the first epidemic wave in the early part of last year. And we have admissions, beds occupied, ICU, and deaths. And then during the second wave, because all the duration of times in hospital has all changed, we decided for the second wave to fit hospitalizations throughout the entire pandemic, but fit only the other data streams for the second wave. And with the third wave, we're doing something similar, but I'm more going to talk about the past work. And the model goes up, as you see, goes up and down because the transmission occurs only outside of hospital by assumption. So all of these individuals that are infectious, they do contribute to infecting new individuals. So the force of infection lambda depends on the transmission coming from all of these classes here. And you need this transmission because what you see in the hospital is actually a result of the epidemic outside. So we also have a description of the epidemic outside of the hospital. And by changing the transmission rate based on different levels of contacts, we have that the epidemic is first going down, and then by introducing control, the epidemic goes. The epidemic is going up. By introducing control during the first lockdown, the epidemic is coming down. So the transmission rate changes over time as a stepwise function. And so the reproduction number is roughly constant unless you account for depletion of susceptibles, which makes it kind of decrease a little bit over time. And you have different values of the reproduction number depending on how many times we want to change it during the first wave in this column, and during the second wave right here. And these are the different estimates for the probability of going to ICU, probability of dying outside of ICU, and probability of dying inside of ICU during the first and the second wave. The numbers might just change a little bit when we redo this just before submission, but the idea is expressed in kind of this graph. And the reproduction number is changing as a stepwise function. So very high, for example, before the first lockdown, and then it dropped below 1 and so on. So this is just a representation of it. the idea is that this fit is done every week, but this is a representation of what happens if you do it every 2 weeks. And the vertical lines are when we allow the reproduction number to change. It doesn't need to change that often to capture most of what we see. But for example, at the beginning, because the data seems to be going up and only starts slowing down, then there is some information for the model to capture the fact that the infection is actually turning, but obviously there is a lot of uncertainty. And then it's much easier to capture it when it's steadily going down or steadily going up. And this is the time when the second lockdown in November was bringing cases down. And then this was a forecast that was done immediately before the reopening. And we knew that cases would have gone up. So we knew that this forecast was going to be wrong. What was interesting is to see how fast these cases were going up, which is partly due to the B117 variant. So the model has some key limitations. It doesn't have any age structure. And age structure is obviously important because severity depends on age, hospitalization depends on age, and also the vaccination is targeted at different age groups. I will discuss better what the limitations are of this. Because it's only fit to hospital data streams, it cannot really constrain the out-of-hospital epidemic very well. But to a large extent, that is not really necessary if you only want to forecast hospital data streams, which is what we're doing. So we are very aware that we are not, the model is not necessarily well suited to represent the epidemic outside of hospitals, but we know that there are other groups that do that. So we decided to focus on a slightly more refined hospital compartment model. We have an ad hoc change at points in transmission, leading to somewhat arbitrary credible intervals in the reproduction number, and I'll discuss that in a minute. And the hospitalizations, we know that are not infections, and so to some extent, the estimates of R are only informed by the hospital data streams. So we know that they are capturing part of what this reproduction number might be. If there are lots of infections outside of hospitals, for example, in younger people that don't end up in hospital, we are aware that our estimates of the reproduction number might be biased by this. So there are some key benefits. The fact that it doesn't have any age structure makes the model fast and conceptually simple and maximally informed by data because the age stratification is very difficult. So what I mean with this is that we try to kind of privilege some aspects of the model versus other aspects of the model. And because there is a suite of model, then we know we don't need to capture everything. And this model has some limitations, but also some benefits exactly because the model doesn't have any age structure. We can combine multiple data streams for hospitals, and because the model is simple and fast to run, then this allows a careful look at the model fit. If the model were much more complex, it would be very difficult or more time consuming to actually observe how well it fits data. And this is the most conceptually valuable point for me, is that when the model fails, it provides insight. So it is not necessarily useful, in my opinion, or at least not always, to have a model that really fits every little bit of your epidemic perfectly and has a lot of different elements you can play with in order for it to fit the data perfectly. It's much better, in my opinion, to have a model that fits certain aspects very well, and when it stops fitting the data very well, this really tells you something about what is happening. For example, exiting out of the November lockdown was leading to a large number of cases, suggesting that there was infection even before coming out of the lockdown. And the fact that deaths are dropping faster now, likely due to vaccination, is telling us something about how useful vaccination is at preventing deaths. A few minutes on the challenges. There are lots of practical challenges I would like to describe. We'll see how much I managed to talk about during the few minutes I have. But fundamentally, if you have full data, you can fit all of the data streams pretty well. But especially at the beginning, for certain devolved administrations, for example, the data streams were completely different from the rest of England, or for certain regions, some data was better than others. So good luck fitting a model to data when you have some data like this and some data like that. So this is one of the normal challenges. The data is always a bit of a problem. I have to stress that now it's so much better after after the first few months of the pandemic. But at the beginning, it was very challenging. The second point is when you have very noisy data. Although all of these data streams seems to be fitting well, the ICU beds occupied have moments when data was 0, for example, for this particular region or the whole administration. The fact that ICUs are going up and down much more than other data streams makes it very difficult for the model to kind of fit that, because in the model, all these data streams are somewhat linked by the assumptions you make. What happens when you have different rates of decline? For example, these are the hospital admissions and these are the hospital beds occupied, and the model is going to come down at the same speed along all of these data streams. What happens if one data stream comes down at a completely different speed compared to the others? The model will always struggle to fit something like this. And then it turned out that some of this data was actually a result of a double counting some of the hospital beds from some of the trusts, which explains part of it. But at the time, we were able to kind of flag it up as a bit of an issue. There are some unidentifiability issues that I don't think I have much time to go through, but because basically we only observe some of these compartments, that it's sometimes you can fit the same data equally well, whether everything is pushing in one direction or everything is pushing in the other direction. So it's always a bit difficult to kind of fit these sort of models. Changes over time. So as vaccination starts playing a role, the number of deaths is going down faster than the model predicts, and this is an indication that vaccination is effectively working. But obviously that would require changing some of your parameters in the model, which you could do, but it requires fitting more stuff and therefore more unidentifiability issues. And another brief comment I would like to make is a judgment call on the last transmission window for estimating the reproduction number. This is a particularly bad fit, but I think it's, we didn't submit this one, but this is just to illustrate an example. If we allow the transmission to change at this point in time, the transmission rate and therefore the reproduction number for this part of the epidemic here is going to be well estimated, because you have a lot of data points estimating it. So the confidence intervals is going to be very small. Obviously too small, because you might want to have a little bit more uncertainty in, for example, the latest data might suggest that it's not really necessarily coming down exponentially. So one thing you could do is to add more time points and then more change points in the transmission. And if you have, for example, a window of about 3 weeks, like here, the model gives a little bit more uncertainty in the reproduction number at the end, but at least the point estimates, so the way the model is actually fitting the data seems to be quite okay. Forget about this data stream that wasn't fit that well, but at least for the other data streams, it looks the model is doing a pretty good job. But if you want to allow for even more variability, you can have a smaller time window. But the problem at this point is that because the data stream that you have available to the data points that you have available to inform your reproduction number are so few that the model is going to, if the model is not fitting one of the data streams very well, like in this case, it's going to try to overtake, going up again to fit these last data points well. And so although you have a slightly wider uncertainty, the point estimates is going to be completely wrong. And this is a problem that occurs whenever you have data streams that don't really match with each other. And so ultimately, that's the last comment to make, the model cannot really predict the impact of control policies. And this is something that I mentioned before, for example, at this point, but we are very aware of it. So when we reach a situation like this, we tend to explore scenarios of what we expect is going to happen. So I'll skip the rest in the interest of time, and I'll just run to the conclusions. So the science for emergency response is challenging. This is done really quickly. The model, I described the model structure. The limitations is what I spent a bit of time on. Despite lots of data, the fit is challenging, especially if the data streams disagree. And the model is essentially used to read the data for scenario planning rather than prediction in many respects, because it's very difficult to kind of predict something about COVID. But the scenario planning has been absolutely instrumental for policy decisions. And I would like to thank all of the individuals that helped me developing this model, and the other model that I didn't talk about, but and the funders. Thank you very much.
Thank you, Lorenzo. So just to remind you, if anyone has any questions, please put it in the Q&A using the Q&A button in the Zoom panel. Daniel Villela, sorry. So it's great talks, thanks. What can you say about any particular experience in dealing with unidentifiability issues other than fixing or narrowing parameter value intervals?
Thanks, Daniel. It's a really good question. Not much, really. If something is not identifiable, typically you either make assumptions. The best way to deal with it, I suspect, is making assumptions and then changing these assumptions and explore how these assumptions really impact your results. So sometimes the unidentifiability issues don't really represent a problem if, for example, they can't constrain one parameter, but the output you are producing doesn't really depend very much on that parameter. So that's not a problem. But if the output does depend on that parameter, then you have to flag it up. The most honest thing to say is the results depend on the assumptions you make. Offer some scenarios, offer some sensitivity analysis, look for more data or request more data.
Thanks, Lorenzo. And I might abuse my position as chair again to ask a question regarding the model that you presented at the beginning, the hospital, the one using the chest data set to look at hospital, the hospital pathway. And so if I remember correctly, you said you were estimating sort of things like the probability of needing to go into ICU. Is that right? And those, so I was just wondering if your model therefore is able to flag up if, you know, for example, if there's a new variant that's potentially more severe and more likely to lead to an increased probability of going into ICU, is your model able to kind of maybe start picking up early signs that that might be the case?
It's an excellent question, and it goes back to the fact that I was saying the model, by being like, if I have lots of little things I can tweak to make the model fit the data perfectly, that might obscure exactly this issue that you're manifesting. If I have a model that is slightly simpler and it has been fitting the data streams quite well, and then at some point the ICUs are kind of going higher than what the model is predicting, that is suggesting that something is happening. And so picking up a discrepancy between the data that we have and the model fit that was working up to now and suddenly stops working, it's a very strong indicator that something is happening that we can't quite figure out, and then it points in the direction of higher severity, for example.
Thanks, Lorenzo. So in the interest of time, if there aren't any more questions, we can always come back to these points if anyone thinks of questions in the meantime. But anyway, thank you very much, Lorenzo, for a really interesting talk.